All right, so let's continue. So besides of the star schema, we also have a snowflake schema and factor constellations. Okay, for snowflake schema, it's a refinement of the star schema where some dimension hierarchy is normalized. It's like further normalized into a set of smaller dimension tables, forming a shape similar to snowflake. That's why it's called a snowflake schema. For fact constellations, it's multiple fact tables share dimension tables, okay, well as a collection of stars, therefore called a galaxy schema or fact constellation. So let's look at the examples which are more intuitive. All right, so assume this is the star schema, which is slightly different to the previous one, as we now have how many dimension tables? 4, right? We have 4 dimensions. We have 4 dimensions and 3 measures here. All right, and for a snowflake schema, as you can see here, for location, it's actually originally it has location, key, street, city, state, and country. Now it is further decomposed or normalized into 2 tables. One is for location key, street, and city key. Another is city key, city, state, and country. So this is the foreign key, and this is the primary key. And similar for the item, we now decompose it into 2 tables using supplier key as the foreign key and primary key to link these 2 tables. All right. So previously we have mentioned that for star schema we don't do further normalizations on the dimension tables, but here the reason that we do this, okay, there are 2 reasons. One is that this kind of further normalization can further save the space, of course. I mean, but it depends on it depends on the situation, really. I mean, here I think this is not a good one, and this personally I don't think it's a good one or a good choice to further normalize it's here, but the dimension here, but here I think it's a good choice. The reason is that for this one, if you still remember, in the Woolworths example, we have around 3,000 locations or shops, stores, and we have of course we have like let me see, if we take city, so in Australia, city could be something like a council, right? So we have, I don't know, hundreds of councils at least, I guess, right? Yeah, we have hundreds of let's say 500. Well, let me do a Google again. Well, I've made a very good guess. So Google told me that there are 547 councils in Australia. So basically, these are the number of city keys, right? So as you can see, this kind of normalization does not reduce the space too much. Okay, because previously we would have, say, 3,000 times 1, 2, 3, 4, 5, and currently we have 3,000 times 3 plus 500 plus times 4. You can do the math by yourself, but essentially it's about 3,000 times I think 3.6 or something. Yeah, not save much of the space. On the other hand, this one is different because, say, we have for items we have 100 1,000 items or even millions of items. But for the supplier, usually we only have hundreds of suppliers. I think that is kind of a good guess, I guess. Even for 1,000, okay, even for 1,000, you can do the similar mathematics, and you will see that it can indeed save much more time compared with this one, relatively. Okay, relatively. So another reason is that another good advantage about this normalization is that it can actually speed up the update, because we don't need to update each and every for each and every updates. We do not need to update all the columns, all the columns. Okay, but it is not this property or this advantage is not useful in a data cube or in this kind of data warehouse modeling, because when we do the updates, okay, first of all, in data warehousing we barely do an update. Okay, so what we do is usually the insert of transactions, which we can only operate on this sales on this fact table, okay, rather than on those dimension tables. And when we do the so we barely do any update, especially on the dimension tables, because dimension tables are more static. Okay, so that's why this snowflake schema is carefully to choose to use them, because they're not always good than star schema. Okay, and for the fact constellation, sometimes, you know, for example, we may have different department, and each department may have their own data warehouse or have their own data at least, right? And on the other hand, I mean, certain dimensions can be shared by different departments. For example, time and maybe branch, right? Item or location. In this example, I mean, these four. Let me see. Yeah, time. Yeah. Okay. Key. Item. Time, item, and the location are the dimensions that can be shared between two departments. One is sales. One is shipping. Okay. So as you can see, we don't need to create multiple dimension tables as long as they can be shared by different departments. Although we still need a fact table for each and every department. Okay, and also here, this is a good example that for the fact table, there are two columns. One is from location and one is to location, where they can actually share one dimension table, as long as, you know, the dimensions and the range of the locations are the same, right? They can share the same dimension table, and this can be done in a star schema as well. Okay. Of course, I mean, for shipping fact table, it has a shaper, which is a dimension that uniquely owned by the shipping department, and for the sales department, the branch is uniquely owned by sales department. So this is the idea of the fact constellation. Right, so there are several advantages of the star schema. First of all, the facts and dimensions are clearly depicted. Okay, it is not only good for the designers to design the database. It is also, I mean, for for example, the dimension tables are relatively it is easy to comprehend it and write queries, as these things are very clearly depicted. Okay. And also the dimension tables are relatively static. The data is loaded into the fact tables, and usually it is appended into the fact tables, right? Because we need to keep all the historical data, right? So these things, these advantages makes it is easy to for the translation from a SQL query to a data warehouse query, right? This translation is straightforward. For example, if we want to find total sales per product category, right, in our stores in Europe, so essentially, in order to do that, if you still remember the operations of the data warehouse, we have roll up, drill down, slice, dice, and pivot. Okay, so here what we're going to do is actually to do a slice on the Europe, because this is the region that we're interested in. We don't interested in other regions, and then do a pivot on the category, right? On the category, because we want to have the total sales per category. In order to translate this into a SQL, it's kind of easy. We first decide which are the tables that needed to be joined together. So sales, of course, this is the fact table. We always need to have the fact table, and then product table, because we need the product category, right? Location, because we need to do the slice on Europe, which is a specific location, right? Then we do the join. So this line is to do the join, and this line is to do the join, right? And then we do the slice, where we specify the region to be Europe, and we do a group by. Okay, we do a group by and select the sum. So this is what we do for a SQL query in order to achieve such kind of data warehouse queries. And as you can see, it is straightforward enough, right? Easy enough for you to figure it out with this star schema, with this star schema. Now let's look at a little bit more about the query language. Although we're not going to cover very detail on this topic. So we only have this slide, which is to give you some initial idea about the query languages for data warehouse. So basically we have, because we have two different approaches using a relational database and a multi-dimensional technology respectively, hence we have two different approaches or two different query languages. One is SQL for relational database, and one is MDX for multi-dimensional technology. Okay, and for SQL we may need some extensions such as cube, pivot, or unpivot. I mean, this kind of extensions or operations are supported by many database systems nowadays, rather than several decades before. Okay. So assume that the operations we want to do is to do a slice on Europe, right? A slice on Europe, and then a pivot on a category and the amount. Okay. So the left-hand side is SQL and right-hand side is MDX. So for MDX, it's even more straightforward than SQL, right? So what we do is it's still like a select from where syntax, but for from, it's always the data cube. Okay, it is sales here. And for where is where we do the slice, right? So it's on the Europe, and for select, right? It is where we do the pivot, right? So we have pivot on category and amount. So we need to decide which is on rows and which is on columns. And here, because as you can see, it's in fact it is a set. So you can put multiple, say multiple. Here should be the levels. Yeah, multiple levels in or multiple elements in this set, and then do the pivoting. Okay, and on the left hand side, it is similar. I mean, we need, just as what we did before, right? We need to know which tables do we need to involve in order to answer this query. So we need sales, product, location. We need to do the join. We need to do the join again. This is the slice, and this group by and select, do the pivot. Okay, do the pivot. And as for the result, right? For example, if we look at the MDX here, so basically we select categories as rows. So the rows should be categories, say C1, C2, and so on, right? And for each category, the column is the amount. So this is the amount. So we can put different numbers into here. And if say we have put another, let's say if we put cost as the second element within this set, right? So we will have another, say another column in the result table, right? And the numbers here. Okay, so that's pretty much it. And you can do the similar things. I mean, you can imagine for the SQL what the output would be. So in general, the very similar. I mean, it's just two columns with which are the category and the amount. Okay, so it's category and the amount, and this is C1, C2, and so on, and these are the amount. So very similar to the result, although in slightly different forms, but that doesn't matter. Okay, that doesn't matter. All right, so before we have discussed the conceptual model, the logical model, right, which are the schemas. Now let's look at the physical model and how do we and the query processing techniques, right? So for the physical model and query processing techniques, there are two main approaches. Okay, one is using relational database technology, and one is using multi-dimensional technology. And there are also hybrid, say, approaches. Where for base cuboid, we use relational database technology, and for other cuboids, we use multi-dimensional technology. If you still remember if we draw the lattice, right? If we draw the lattice, So this one should be the base cuboid, which contains all the dimensions, right? All right. So so let's look at some query processing techniques. Okay. One is to do the selection on low cardinality attributes. Let's look at the example first. Okay. So here we have 3 dimensions, right? We have 3 dimensions. We have this fact table and customer location and time. Now assume that we want to do slice on region to get those data for those data in Europe. All right. So what's the problem of such kind of operation, right? One is that the fact table is quite large. Okay, say 1.6 billion, if you remember. So if we want to do this kind of slice, we need to go through each and every transaction, and we need to do the join. Yeah, this join. Okay, we need to do the join. Then we can have those transactions with region equals to Europe. That's the typical way of doing it. But if you still remember in database, in relational database, we can build indexes to help on this kind of operations or this kind of tasks. Now in data warehouse, we do have similar technologies and specifically designed to fulfill our needs under this special circumstances. Okay, right. So let's start from an example of this bitmap index, as this is the technology that we're going to introduce, and then we will compare it with other technologies that we have learned before. For example, the hash tables or B-tree. Okay. So for bitmap index, it is an index on an attribute with low distinct values. The distinct value are the number of values. The number of different values. Okay, the number of different values. So we want to have a low number of different values on this kind of attributes or columns. For example, in this table, arguably region is a good choice, as it has three different values in this small table. But you can imagine even you consider a large table and a company that have departments all over the world, it will still have only 7 distinct values within this column, right? And for type is similar. We have a retail and dealer, 2 types. But for some other attributes or columns, for example, if it is say supplier name, okay, we expect to have millions, no millions, but thousands or tens of thousands suppliers, then that is not a good column to do bitmap index. Okay, now for each distinct values v, we associate it with an n-bit vector, where n is the number of rows. Okay? For example, in this table, for each distinct value v, which is Asia, Europe, and America, we have a bitmap. A bitmap where each bit, or not each bit, where each vector is an n-bit vector, this n dimension, where n is the number of rows. Because here we have 5 customer, so it's a 5-bit vector. Okay. As long as we have a bit vector Okay, I mean, apparently, this 1 or 0 indicates that so this customer belongs to this region or belongs to this value or not, right? So we take the leftmost as the first customer. So this is C1, C2, and so on. So 10100 means we have a C1 and C3 associated with Asia. Okay, as it belongs to region Asia. And for the other three, because they're 0, that means they're not, the region is not Asia. Okay, so the ith bit is set if the ith row of the table has the value v for the indexed column. And multiple bitmap index can be efficiently combined to enable optimized scan of the table. Well, we discuss this later, but let's compare this one with what we know, what we have already known, for example, the hash table. Okay? So in hash table, what we do is we first list the hash keys. Here should be Asia, Europe, and America, right? And for each hash key, we actually maintain a list. So this is C1, this is C3, this is C2 and C5. This is C4, right? So you can do the computation. See here, if we take the hash table into two parts, right? This part are the keys and this part are the values. So the number for the values, the total number of elements here is the total number of rows, which is n. And for each here, for each one, we have to use so usually when we use it really depends on how many different rows do we how many rows do we have, but let's say we use say 2 bytes for each of them. Okay, so it's n times 2 bytes. N times 2 bytes. But here we only need 5 bits for each distinct value, right? So it's 5 bits. It's in fact n bit. It's in n bit. In bits times number of distinct values. So this is what we have. In the example here, it should be 3n bits, okay, which is 3n divided by 8 bytes. And what we have before is 2n bytes. So you can see the differences here. So as long as that's also why we want this column has a low distinct values. Okay, if you do the math, you would see that when the number of distinct values grows up, the space cost of this bitmap index will be more than that of the hash table eventually, right? Because for the hash table, it's kind of a fixed number given a fixed number of rows, so it's always 2n bytes. But here, say this is if we have more than 16 distinct values, right? Then we would have more than 2n bytes. We will need more than 2n bytes to store this bitmap index. So as the left part are the same, so we don't take the left part into consideration. Right? So that's why we need low distinct values. Multiple bitmap index can be efficiently combined to enable optimized scan of the table. Because consider the operation between 2 bit vectors, right? For example, if the query is to find, say, we want the number for Asia and Europe. In a hash table, you need to merge these 2 lists, but in bitmap index, you simply do an OR. On these 2 bit vectors, right? Then you will have this as the final answer of this query. So so far we have discussed the bitmap index on the column or on the dimension tables. Okay, on the dimension tables. But what we really care about in a data warehouse is those on the fact table, right? Because the IDs on the fact table is what we want to have, or the measures on the fact table is what we want to have eventually. Okay. So this is called a bitmap join index, where it refers to the bitmap index on fact table joined with dimension tables. Okay, we build a bitmap index on fact table joined with dimension tables. Now below is an Oracle example, right? So as you can see, Oracle kind of supports this kind of bitmap index, and also this data warehousing. So you create a bitmap index. Okay, this is the name of the index. You can name it whatever you like. On sales, and this is the key, right? Is the key. It's the column that has few distinct values, right? Is the key. From sales and customer, here of course the sales is the fact table and the customer is the dimension table. Then apparently we need to do a join. Okay, we need to do a join. We join these 2 tables by the customer ID, which is the primary key of the customer, and the here shouldn't be a S here, and the foreign key of the sales, right? So conceptually, we perform a join, right? Map each dimension value to the bitmap of corresponding fact table rows. It could be easier to understand with this example here. So basically, if you still remember, we need to perform a join first. Okay, well, we perform a join first with this customer and this customer ID, right? So after that, we would have say this is region, this is type. We would have this C1, so it's Asia retail. This is Asia retail. This is Asia retail, and so on. Okay, you can fill the. So this is Europe dealer. Europe dealer. C3 is Asia dealer. Right. C4 is America retail and Europe dealer. Okay, so this is the joined table, right? You join the fact table joined with dimension tables. This is the new table you had, and then we need to build the bitmap index on it. Okay, sorry. We map each dimension value to the bitmap of corresponding fact table rows. Okay, the key here is now we'll map them to the fact table rows, not the dimension table rows. In the fact table, we have how many rows? We have 8 rows, right? We have 5 rows here. But since we're going to map the values here to these 8 rows, we need a bitmap with bit vector of 8 bits, right? Of 8 bits, as you can see here. It is no longer 5 bits. And I mean, you can see here, this Asia, we have Asia, and Asia here. So it's the first, second, fourth, and fifth rows in the fact table corresponds to the to these 4 bits in the bit vector, and we do the same for Europe and America. We would have a bitmap index or a bitmap join index on sales with the key is customer.region. All right. Okay, so we may stop here for today. Tomorrow we're going to continue introduce other say index methodologies. For example, as we now introduced those for attributes with low distinct values. We will consider high cardinality attributes, right? And say arbitrary selections on dimensions, or we do have other kinds of operations that can be supported by different kind of indexes, okay, in data warehouse, right? So that's all for today. We will continue on tomorrow.